Okay, we have two charges here. Let's look at electric force between them again. So we know our equation, force electric is equal to K absolute value of Q1 times the absolute value of Q2, all divided by radius squared. So let's say these are two conducting spheres that are metal conductors. So let's give this one here, I don't know, let's say it's a 3Q charge here. Okay, and let's give this one here a negative, let's say negative 5Q. Remember, those charges will be residing on the outside of these, but we will measure the distance from the center of this charge to the center of this charge over here, even though the charge is residing on the outside. And again, we'll calculate the radius between the two of them from center to center. So then we'll just use this equation here. Okay, to calculate the electric force, whatever Q is, you would take 3 times that and 5 times that Q, and then multiply by your K constant and divide by the distance between them squared. Okay, now what if these spheres are the same size, so what if I was to take a conducting wire, okay, and connect it between the two? So here I go. Here's my wire there going all the way across. Okay, and I allow it to conduct electricity across, and then I will remove the wire after I'm done. So what would that do? Well, what's going to happen is these charges are going to average. Electrons are actually going to flow, okay, until we neutralize this charge here. Okay, and that'll leave a negative 2 left on here, and then that would distribute, okay, when you were done. So what would the charge on both of them be? So the easy way of doing it is just take 3Q plus a negative 5Q and divide by 2. So what's going to happen is we're going to be left with, that'd be a negative 2, right, divided by 2. We're going to be left with a negative Q, okay, on both of these spheres. So let me write that in red here. So a negative Q here and a negative Q here. Okay, and then we can recalculate our force electric between those. So now it's going to be K times Q over R squared. Okay, and before it was 3Q and a 5Q, so it looks to me like the first electric force would have been something times a 15, and then let's call the rest of it a K value, because we'll have that and then divided by R squared. Okay, so K represents all the rest of the stuff that's in there. Okay, and when we redo this calculation, we'll have a 1 times a 1, so we'll be left with a K value there like this. And it looks to me like we have decreased the electric force between those by a factor of 15. Because again, you would have had a 3Q here and a 5Q here, so that's a 15. The K constant here in the R squared does not change, and that is what's represented by this K here. Okay, and likewise here, we would have a 1Q and a 1Q, and therefore just a K left over. So again, if you put a conducting wire across it, you're going to allow charges to flow until they're the same on both, since the spheres are the same size. Okay, now what about those parallel plate things again? So reminder, our equation is volts is equal to ED. And let's say I've got 16 volts on this plate, and I've got 4 volts on this plate here. So in this case, our ground is not 0. Remember talking about this when we did potential energy. Sometimes ground is not 0. So the potential difference across these plates is 16 minus 4, so it's 12 volts. Okay, so if I know my distance between these plates, okay, let's just say it's, I don't know, 5 centimeters. Pretty big distance there, but whatever. I can go 12 is equal to E times 0.05, like that. Okay, then I can calculate my E value. So now I know my E value across these plates. I'll let you actually solve that if you want to. So what about the voltage as I go across? Okay, well, if I know my distance, let's say I go from here, from this plate, and I travel, let's say, 1 centimeter. Okay, then how do I get my volts at this position here? Again, I know my E value there, right? Okay, so then I can say volts is equal to whatever E value I have there multiplied by 0.01, because I've only traveled 1 centimeter. Okay, and of course if I'm halfway there, let's say I'm right here, well then I know I've got 6 volts there, right? Okay, because 12 volts is the whole distance across there, so I know that I'm half of the distance, so therefore I must be 6 volts. So it's a linear relationship, in other words. Okay, because volts is equal to E times D. Okay, so, and notice I'm getting a potential rise as I go this way, so notice how it's positive. If I go this way, the potential is actually a falling going on here. So I would start at 16 volts here. Okay, and that would go downwards this way, right? So there you go. Now what if I wanted to know my absolute voltage here? Okay, so a reminder that whatever volts is here, I've traveled 6 volts, right? But remember, my 0 is not 0, it's 4. Okay, so then I have to add plus 4 to this, and I actually get 10 volts here. Okay, and likewise here, if I travel 1 centimeter to here, I would get my volts, but remember I'm at 4 volts, so I must add a 4 to this position also. So everywhere I go, I must add a 4, okay, because I did not start at a 0. Okay, but I know there's 12 volts across these. So if I go halfway there, I know I've gained 6 volts of potential, but I didn't start at 0. Okay, so let's say moving 1 centimeter gives me 2 volts that I've gained here. But remember, I started at 4, so add that to that. So use this equation once I find the electric field to find whatever voltage I have, and then add 4 to it. And that's how you do that question.